2, we will continue to speak about exponents. However, we will talk about 0 and negative exponents. In this lesson, you will study how to use the multiplication properties when working with negative exponents. And this slide, you can tell, is the activity that we will be doing in class to start to see the patterns that form. Moving on, we now can establish the definition of 0 and negative exponents. If your number was a, we're going to let the variable a represent your number, be a non-zero number, and let n be the positive integer. Then a non-zero number to the power of 1 is a to the 0 equals 1. And that is only if it does not equal 0. If we have a to the negative n, that is the reciprocal of a to the nth power. So a to the negative nth equals 1 over a to the nth. And again, that works only when a is not equal to 0. So in example 1, our first question is, what's 2 to the negative 2? So 2 to the negative 2 is the reciprocal of 2 squared. So 1 over 2 squared would give us 1 over 4. Our next question is negative 2 to the 0 power. So, that's very tiny. If a to the 0 power is 1, then the answer for this one is also that 2 to the negative 0 is going to be 1. Okay, if a to the 0 power is 1, then negative 2 to the 0 power would also be 1. In our next examples, we have 5 to a negative x. So the exponent is the exponent is negative. So again, that means it is the reciprocal of 5 to the x power, which we could write as 1 over 5 to the x power. In letter D, we have 1/3, but that's going to be raised to the negative 1 power. And again, if we raise to a negative, the reciprocal of 1/3 is 3. So our answer would be 3. And in letter E, we have 0 to the negative 3. And if you remember our rules, we said a cannot equal 0. So that means 0 has no reciprocal. So this answer is undefined. Moving on to example 2, we're going to simplify exponential expressions. So this time we want to write these with positive exponents. Okay, so 5 times 2 to the negative x is the same as saying 5 to the reciprocal of 2x, and that would be 5 halves to the x power. In letter B, we have 2 negative exponents again, so we will be doing the reciprocals to those. And we will get 2 times 1 over x squared times 1 over y squared, which would give our numerator 2 over x squared y squared in its simplest form. So my study tip looks like it got a little cut off here. It says, informally, you can think of rewriting expressions with positive exponents as moving factors from the denominator to the numerator or vice versa. So one we have not seen on this page yet is 1 over 3x to the negative 4. If we want that to be positive exponents, we would just switch the x to the 4th, because that is what is to the negative 4, to our numerator, and 3 would stay as the denominator. In example 3, continued, we have 3 to the negative 2 times 3 squared. So we remember our rules again. We're going to use the product of powers property first. We have the same base, so we can go ahead and add those exponents. So when we add those exponents, we get 3 to the 0 power. And we know anything to the 0 power is going to be equal to 1. In letter B, this time we have 2 to the negative 3 raised again to the negative 2. And this time we're going to use our power of a power property. So we're going to go ahead and multiply our exponents. A negative 3 times a negative 2 would give me a positive 6, 2 to the 6. And because we can go ahead and simplify that further, we will do that. And 2 to the 6 is 64. Continuing our example 3, this time we have evaluating the expression 3 to the negative 4. And this time you might want to evaluate with a calculator. Here are the keystrokes that you would use on your calculator. If you have any kind of a scientific calculator, we can have 3, then you use the y to the something power. You type in your 4, and you go ahead and use the positive negative button, and then an equal, and your display will show you it in a decimal form. In example 4, we're going to simplify exponential expressions by rewriting with positive exponents. To rewrite 5a to the negative 2, we will use our power of a product property again, and we will take each one of those and we will multiply them. 5 to a negative 2 and a to a negative 2. We don't want any negative exponents, so we need to write the reciprocals. Those reciprocals would be 1 over 5 squared and 1 over a squared. And it looks like I don't have my answer to pull out there, so we will go ahead and we will simplify this further. We can multiply our numerators, which is 1, and we can multiply our 5 squared here, giving us 25a squared as our denominator. And the next one, we will do 1 over d to the negative 3n. To write that with the definition of negative exponents would be the same as d to the negative 3n to the negative 1. The negative 1 here as our final raising exponent is what gave us the same as this value here. Let's go ahead and underline it. This value as the denominator, we can go ahead and change it to a negative exponent. Now we can apply our power of power property, which would be d to the negative 3n times negative 1. And we can multiply our exponents. A negative 3 times a negative 1 will give us a positive 3, and we still have our n. So it would be d to the 3nth power. I'm going to pause just in case we don't have enough time for the next goal. Part 2 of 8.2, we talk about the graphing of these functions. So if we have used the expression of the form b to the nth, where b cannot equal 0 and n is an integer. To model some situations, we need an exponential function of the form y equals a times bx, where x is a real number, b is greater than 0, and b cannot equal 1. To graph the exponential function y equals a times b to the x power, make a table using integer values for x and plot the corresponding points. To complete the graph for all the real values of x, connect the points with a smooth curve. This would look like this. So if we put x in as negative 2, then we would have 2 to the negative 2, which is the reciprocal because it's a negative. So that would be 1 over 2 squared, or 1/4. We can also do that again with negative 1. We would have 2 to the negative 1. This time we have, again, a negative exponent, which would give us the reciprocal 1/2. If we put in 0, as our exponent, it's going to equal 1. If we put in 1, that would be 2 to the first power, which is 2. 2 squared, 2 cubed. So you'll notice that each one of those points are plotted, and to connect those points, we would make a smooth curve. Now in real life applications of y equals ab to the x is often the time period, as in example 6. A professional basketball player's first year in the NBA was 1998. Suppose it were estimated that from 1998 to 2010, his average points per game could be modeled by points equal 18.5 times, which is 1.038 to the exponent, we'll use t here, where t is 0, representing the year 2000. So estimate the player's average points per game in 1998. So we're going to go ahead and we're going to substitute -2, because that's 2 years earlier than the year 2000, for t. And we can go ahead and that would look like this. Points, 18.5 times 1.038 to the -2. And this time we'll just use a calculator, but that would be, that would again change that to a fraction form. And that means that gets you to 17.17, which means in the year 1998, his average points per game were about 17.2 points. This time we're going to estimate his average points per game in the year 2000. So we're going to substitute 0 for the time. So again, we have points equals 18.5 times 1.038 to the 0 power. And remember, anything to the 0 power is 1, so that would equal 18.5. So here we have, in the year 2000, his average points per game were 18.5 points. He has increased his points per game since 1998. And that concludes the lesson for 8.2.